fine now?
Go ahead and start.
Okay, so we have two problems to go over. This is the second test. Problem 1, spin 3 particle. Okay, so we have spin 3 particle, that's important, okay? Is in a state where there's 64% probability of obtaining as z equal to 2h bar. All right, this corresponds to the state what? State 3,32. Okay, let me remind you, this is my S and this is my M number, right? Okay, and this is 3,2. And 36% probability of obtaining as z equal to h bar. So that corresponds to for the particle in state 3,1. Okay, and then there is another piece of data given. The expectation value of Sx is also given, and we're going to need that later on. Okay, well, first we see that the particle may only be in state 3,2 and state 3,1. There is no other states possible. Although, in general, for spin 3 particles, there are, we know, it's going to be 7 states, right? 2s plus 1, 2 times 3 plus 1, that's 7. But we only have 2 for this particular particle. That state only consists, it only contains 2 basis states, which is 3,2 and 3,1. So we can start with that. We can say that the psi, okay, is a linear combination of 2 states. 2 states, and that is state 3,2. All right, and then state 3,1. Okay, now what are the coefficients? That's the whole idea of this problem. We need to figure out the coefficients. Okay, if the chance to be in 3,2 state is 64%, right? That means that essentially what we're talking about, the coefficient next to 3.2, the absolute value squared of that coefficient is 64 over 100, right? So that means the coefficient itself, absolute value squared, is square root of that, right? Which is 8 over 10, right? Or alternatively, it's just 4 over 5. Okay? 4 over 5. Do you understand again why is that? Let me draw it somewhere here. So essentially, what I'm saying is that the probability to be in 3,2 state, which is absolute value squared of probability amplitude psi 3,2, is given to be 64 over 100, which means 3,2 probability absolute probability of 3,2 psi is just what? Square root of that is just 8 over 10, which is just 4 over 5. Okay, and that's what I place next to 3.2. All right, now next, a coefficient next to 3.1, for the same reason, you can say, all right, it's 3,1 psi, absolute value squared, is 36 over 100, and that means the coefficient itself, 3,1 psi, is 6 over 10, or you can say 3 over 5. 3 over 5. Am I done? What do you think? I have the coefficients. Well, something is missing. Okay, and what is missing is relative phase. Okay, I can place a relative phase anywhere you want. You can place it here next to 3.2, or you can place it next to 3.1, it doesn't really matter where you place it. Let's put it next to 3.1. We have because I have more space there. So I will say that the coefficient, the probability amplitude for the particle to be in 3.1 state will be 3/5 times some relative phase, e to the I theta, which is the relative phase. Now, the challenge now is to find that relative phase. That's what we are going to do for the rest of this problem. Okay, that's the idea. And how do I get out of this? Probably like this. Okay, now, yeah. Okay, so now we need to figure out the relative phase theta. This is really similar to one of your homework problem in chapter, I think, 1. This is where you were given some information about some probability amplitude, or what was that? It was expectation value was given, and you really need to find the coefficient, the state. So you were using that additional piece of data to figure out the relative phase. Okay, so we pretty much already used up the information that we had about the probability of being in 2H state, as z equal to 2H bar, and as z equal to H bar. So we already used that information. There's nothing else we can get out of it. But we have another piece of information which we didn't even touch yet. That is the expectation value for Sx. So we somehow need to figure out how to use that piece of information so far. In order to do that, we need to express Sx in terms of unknown theta. So how do we do that? Let's first figure out what is the action of Sx on our state psi. Okay, if I can figure out what is Sx psi, then I can easily calculate the expectation value for Sx, but by simply multiplying that by psi bra. All right, so that would be equal to Sx. Again, I don't really know what's the action of Sx on this one, but I can express it in terms of raising and lowering operator. So it's going to be 1/2 S plus S minus acting on state psi. That's what Sx psi is. Okay, let's expand this, and I will express that now. Okay, hold on a second. It's probably on my equipment here. So that will be Sx psi is 1/2 S plus S minus acting on 4/5 3/2 plus 3/5 e to the I theta 3/1. Here you go. Now we apply raising and lowering operator to the states. We remember how to do that, don't we? Huh? So 1/2. Now let's apply let's say raising operator first, and then lowering operator. It doesn't really matter in which order you do that, obviously. No, like this. Okay, so it's going to be 4/5, and then what's that? H bar. We apply and raising to 3/2. So it's going to be H bar, and here S times S plus 1. So 3 times 3 plus 1 minus M times M plus 1, which means 2 times 2 plus 1. Okay, square root. And that would be state 3/3. All right. Plus, now raising operator applied to state 3/1. First I would write the coefficients. Okay, now apply raising operator to S31 and I get, okay, S plus 1. Oops, what I meant is 3 plus 1 here, minus 1 times 1 plus 1, square root, and I get state 32. Plus, now applying the lowering operator to state 32, so it's going to be 4 over 5, h bar, and that's 3 plus 1. Why did I say S? 3 plus 1 minus 2 minus 1 square root, and the state is going to be 3, 1. And then finally plus 3 over 5 e to the I theta h bar 3 plus 1 minus 1 minus 1 square root, and the state is going to be 3, 0. Alright, I hope I didn't make any algebraic mistakes here. That looks like correct expression. Now let's do the algebra. Let's do quick algebra here and see what is this. That's 12 minus 6. So this is a square root of what? 12. Oh, I'm sorry. Square root of 6. I should be careful. 6. 12 minus 6. Yeah. That's 12. The second one here is square root of what? 12 minus 2. So square root of 10. This one is also square root of 10. And then this one is square root of 12, I believe. Yeah. So let's write it down in a little bit more compact way. And I can also factor out something that is in common. What is in common? I can factor out h bar. I can factor out 5, so it's going to be 10 outside. And what do I have here? 4 root 6, 3, 3. Plus 3 e to the I theta root 10, 3, 2, plus, what else? 4 root 10, 3, 1, plus 3 e to the I theta root 12. Something is missing. Root 12. I forgot to write down the state itself. 3, 0. Yeah, like this. Okay, now it's all correct. Okay, so that's my Sx acting on state psi. Now, what is the expectation value of Sx? Sx is just the sandwich made with Sx, right? So that means whatever I just calculated, I need to multiply it by psi bra. So that will be, what's that, 4 over 5, 3 over 2. So we make bra out of this cat that we have here. Obviously, I'm going to complex conjugate the relative phase. Don't forget that. And we multiply it with psi. Oh boy, I need to copy this now, right? Okay, let's calculate. Let's copy that here. 4 root 6, 3, 3. I don't really need to copy all of that because you know that some of them will not really matter. But for completeness sake, I'm going to copy that. Okay. Okay, so that is really easy to calculate. 3, 2 bra will find 3, 2 cat, and will produce what? Will produce 4 over 5 times 3 I theta root 10. Am I right? Yes, 4 over 5. So essentially that is this multiplying this. Right? Yeah. And
h over 10.
oh yes, I forgot h bar, of course. Somewhere here, this should be h bar. Oh yes, h bar with 10, that's correct as well. Thank you, times h bar with 10. Yeah, and then plus the second part is going to be this 3, 1. Bra will multiply 3, 1 cat. And this would end up be 3 over 5 e to the negative I theta, okay, times 4 root 10 times h bar over 10. Okay, so let's factor out the common parts to all of it. So you end up with 12 root 10 times what h bar and what divided by 50. And if I factor e to the I theta plus e to the negative I theta here, okay, I would like to rewrite this like that. I would say, okay, how about dividing this by 2, and that allows me to, let's get this 2 out, let's borrow this 2 out of 50, and so this 50 becomes 25 now. Why did I do that? That's because that thing in the parentheses, according to Mr. Euler, becomes a cosine theta, right? Okay, so that becomes 12 root 10 h bar over 25 times cosine theta. Now, according to the problem, this is given to us, and it equals to negative 12 root 10 times a divided by 25 times h bar. That's given.
Wait, shouldn't that? Oh, yeah.
I'm sorry, what? I didn't hear. Can you repeat? So that really tells me that the only way for me to make that equal to given value, right, is that my cosine really has to be equal to negative 1. Okay, so I get the cosine theta has to be equal to negative 1, which means theta equals to pi, right? So that's pretty much it. I'm ready to write down the answer, which means the state psi is 4 over 5, 3 over 2, plus 3 over 5, e to the I pi, 3, 1. Or, to make it even easier, I mean, you know, e to the I pi is negative 1, so it's 4 over 5, 3, 2, plus, actually minus, hold on, because it's negative 3 over e to the I pi is negative 1, so it's minus 3 over 5, 3, 1. This is the answer. That is it for this part of the problem. Now, for some reason, I don't know why, this problem turned out to be very challenging. I mean, I know that most people somehow miss this part for some reason or another. I don't know why. But yeah, that turns out to be a challenge. What can I say? I mean, that's unfortunate. Do we have any questions regarding this part of the problem? No questions? Okay, so then we can continue. Let's move on to the next Oh, next page is empty. Let's skip that. Here you go. Next part. Calculate Sx squared. Well, calculate Sx squared is that's expectation value of the square of x component. All right. Essentially, what we need to do is, let's normal Sx squared. This is expectation value of Sx times Sx psi. I can rewrite it like this. We know what the action of Sx operator on psi is. We calculated that in previous part of the problem. By the way, if you got the first part wrong, obviously this one will be wrong as well, but we didn't take points for that in this part of the problem, so you shouldn't be penalized twice for having Sx psi wrong in the first part of the problem. Anyway, so we already know, let me copy from the first part of the problem, that we calculated that Sx psi is, what's that? That is h bar over 10 for root 6, 3 plus 3 root 10 ei, you can say pi, it doesn't really matter, I can keep theta, it doesn't matter, it will cancel out, 2 plus 4 root 10 1 plus 3 root 12 ei pi 0. Alright, so then Sx expectation value squared is just that state, if you convert it to bra, multiplied with this ket. That's all. Let's convert that state to bra, so you get h bar over 10. What doesn't write anymore? H bar over 10. And now here it's 4 root 6 3 bra plus 3 root 10 e to the negative I pi. I know it's negative 1, it doesn't matter. This would be same thing if theta is whatever. It doesn't have to be pi, it will still cancel out in this case. Alright, plus 4 root 10 1 plus 3 root 12. What happened? E negative I pi 0. Okay, and then I just multiply by this ket, h bar over 10. Oh, now I'll copy all this. 4 root 6 3. You understand that I'm writing actually more than I have to in this problem, but hopefully it will make it more clear. All right, here it is. Now the fun part. Let's multiply h bars. H bar squared over 100, and now okay, I hope I don't need to explain here much. It's going to be 4 squared times 6 plus 3 squared times 10 plus 4 squared times 10 plus 3 squared times 12. That's it. Yeah, you guys, then do you understand this part? Because this is really, I hope I don't need to go into more details here, right? So that will be equal to what, 16 times 6 plus 9 times 10 plus 16 times 10 plus 9 times 12. This ends up to be h bar squared times 454 over 100. Okay, So that is just 227 h bar squared, whatever it is, over 50. Okay, that's it. Let's move on. What is the uncertainty delta Sx? This is the square root of expectation value of Sx squared minus the expectation value of Sx squared, like that. So that will be square root of 227 h bar squared over 100 minus, now expectation value of Sx was given in the first problem, at the beginning of the problem, so it's 12 root 10 over 25 h bar squared. So if you do this simple algebra, you will end up with h bar over 5 times square root of 559 over 10. That's it. Any questions? No questions? Was it too hard? No? Should it be not 227 over 50? Oh, yes, you're right. Thank you. It should be 50 here. Absolutely, yeah. I copied it wrong. Yes, thank you. All right, yeah. Okay, so is there any other questions? We move on to the next one. Next problem. Okay, if there's no problem with this, let's move on to this next part of this then. This is the second problem. The Hamiltonian for a spin 1/2 particle is represented by this matrix. E0 is some constant with dimension of energy. Particle is initially in that given state. This is just plus z state. Determine the state of the particle at time t, which means evolve the particle state in time. Again, in short, remember, how do we do that? What's our algorithm? First, we find eigenvalues of the Hamiltonian. Then we find eigenstates of the Hamiltonian. Next, we will represent given initial state psi at time 0 in the basis of eigenstates of the Hamiltonian. Then we evolve that initial state in the basis of eigenstates of the Hamiltonian, which is piece of cake, and then we switch back to original basis. Okay, let's do that. Okay, so the first item on our agenda is find eigenvalues of the Hamiltonian. Okay, so what do? We find the determinant, calculate the determinant of 2 minus lambda I, negative I, 2 minus lambda, which means we subtract lambda from the main diagonal. Okay, we find the determinant of this matrix, set it equal to 0. That's called circular equation. We done it many times. So how this equation looks like? It's going to be 2 minus lambda squared, right? Minus what do we have here? Negative I times I, and this equals to 0. So we end up with 2 minus lambda squared. It's going to be minus 1, so it's going to be equal to 1 on another side. Now we can take square root of both sides, so it's going to be 2 minus lambda equals to plus minus 1, right? and that means that lambda equals to 2 plus minus 1, which is 3 and 1. So what are the eigenvalues of the Hamiltonian? Well, here you go. Eigenvalues of the Hamiltonian are 3 E naught and Y E naught. Remember that that our Hamiltonian has some constant that multiplies this matrix, and we kind of factored that constant out when we calculated the eigenvalues of this matrix. So we've got to multiply. Essentially, that constant multiplies every a matrix element in that matrix representation. So we just, for the sake of simplicity, didn't we factored it out in our calculations, but eigenvalues actually, they do have E naught there. Okay, so next item in our algorithm is eigenvalues, right? Now find eigenvalues. Okay, first we find, whatever, it doesn't really matter. Let's find eigenvalue corresponding to why do I say eigenvalues? I'm sorry, you should correct me. Eigenvectors, thank you very much. Yes, that's absolutely correct. What I meant is eigenvectors, because I already know eigenvalues. So let's find eigenvector corresponding to eigenvalue 3 E naught. Let's denote that eigenvector as 3 E naught ket. That's what we're looking for. We're looking for 3 E naught ket in SZ basis, which is the basis we're working at. That corresponds to lambda equals to just 3. Okay, so, let's plug 3 for lambda. 2 minus 3 I, negative I, 2 minus 3, I'm just plugging 3 for lambda, multiplied by some vector x1, x2, has to be equal to 0. Alright, so that means what? Negative 1 I, negative 1, x1, x2 has to be equal to 0, 0. If I will multiply the first line by my vector, so you get negative x1 plus I x2 equals 0. Or that means that x1 essentially equals to I x2. So my vector 3 E naught ket in SZ basis, which is just this vector x1, x2 I'm looking for, right? It equals to what? Well, I can take x2, let's make it easy. If I take x2 to be negative I, for example, then x1 is going to be 1. And normalization, remember normalization? So this part I would probably skip. You probably know already by now how to normalize this. It's 1 over root 2 to make this vector properly normalized. Okay, so we're done with the first vector. The second vector, remember our lambda over here was 3 and 1, which means our eigenvalues were 3 E naught and just 1 E naught. So my second eigenvector of the Hamiltonian is just 1 E naught, which corresponds to lambda equals to 1. Let's find that. So we plug 1 for lambda, 2 minus 1 I, negative I, 2 minus 1, multiplied with 1 x1, x2. equals 0, 0. Alright, so that means 1 I, negative I, 1, x1, x2 equals 0, 0. Okay, let's multiply the first line by this column. You get x1 plus I x2 equals 0. Or you can say that essentially x1 equals to negative I x2. So that means that my vector E0 in SZ basis, this x1, x2 vector is, now if I choose x2 to be I, then x1 is again 1, and normalization 1 over root 2. Remember, if you choose x2 to be something else, it would not really change anything. It will just multiply the whole vector by overall phase, which will still produce the same vector. By the way, let me remind you, why do I multiply the first line by this vector, not the second? It doesn't really matter which line you multiply, which line of the matrix you multiply. If you multiply the second line, you will get the same answer. It's just multiplying the second line by this vector will not get you anything extra, anything new. Alright, so now we have those two vectors in SZ basis. Those are Eigenstates, Eigenkets of the Hamiltonian. Okay, now let's move on. Next item. Oops. I need more space. I really need more space here. I think I need to. Oh, here you go. Nope. Just a second. I need to figure out how to do that. I think I know how to. They told me. Here you go. Oh, wonderful. I think I managed to do that. Only can repeat my success here. Here you go. I got more space. All right, finally. Okay, let's continue. Now I can express my. I need to express given state psi at 0 in terms of eigenstates E0 and 3 E0. Here you go. So how do we do that? Well, E0 and 3 E0 represent a basis. They are a pair of two orthogonal states. They are orthonormal, right? We normalize them as well, so they can be used as bases. So you can essentially, if you you can express the unit operator in terms of those two states. This is the unit operator in the basis of eigenstates of the Hamiltonian, right? If you multiply by psi, that is essentially E0 psi plus 3 E0 3 E naught psi. So what I need to find is those two probability amplitudes. Let's calculate that. So the first probability amplitude E naught psi is what is E naught? E naught was 1I, right? So I can write it like this: 1 over root 2, and you make a bra out of that, 1 negative I, right? Let me, yeah, here is my E naught, so the bra would be 1 over root 2, 1 negative I. Alright, so then I multiply this by 1, 0, and what do I get? I get 1 over root 2. Okay, 3 E naught psi is 1 over root 2, 1 I. Yeah? Times 1, 0. And that is still 1 over root 2. Here you go. Now plug it into psi. We get psi equals to 1 over root 2 E naught plus 1 over root 2 3 E naught. That's it. Now we can evolve it. That's easy. Time evolution, right? Psi t is 1 over root 2. We know that each eigenstate of the Hamiltonian, those are stationary states. They only acquire overall phase. But that phase is different. That is the phase which is particular to each eigenvector. So a state E naught would acquire the overall phase, which is e to the negative I, E naught t over h bar. And the state 3 E naught would get overall phase of negative I, 3 E naught t over h bar. Here you go. That's it. But you know, just for the sake of, I don't know, aesthetics, or to make it look a little bit easier, let's factor out overall phase out of this thing. And in general, what we can factor out of this? Let's factor out e to the negative 2I E naught t over h bar, and also root 2. Okay, so if I do that, what do I have for the first term in this product? It's going to be e to the positive I E naught t over h bar, E naught. Do you have to do this? No, not necessarily. Well, I would like to see my expression to look a little bit better, that's all. Let's check. If you multiply this e to the negative 2I E naught t over h bar by the exponent in the parentheses, you get the original e to the negative I E naught t over h bar. And then plus the second one is going to be e to the negative I E naught t over h bar, 3 E naught. Here you go. Now it looks more or less symmetric, which means better. Hopefully it will transform into a nice sine and cosine later. Okay, next term, we're switching back to SZ basis. Switch back to SZ basis. What do I need to do? Well, I'm just replacing E naught with what? It's over here. It's 1 over root 2, 1, what's that? 1I. And 3 E naught is 1 over root 2, 1 negative I. Yeah, that's the expression for those two eigenstates of the Hamiltonian in SZ basis. And what we get psi, oops, we get psi at time t equal to, do I need to keep the overall phase? I don't have to, but let's write it down for now. Okay, over root 2. And here it's going to be e to the I e naught t over h bar 1 over root 2 1I plus e to the negative I e naught t over h bar times 1 over root 2 1 negative I. Okay, let's write it down. So e to the negative 2I e naught t over h bar. Now, how about root 2 times root 2? I can factor it out. It's just over 2. And this becomes e to the I e naught t plus e to the negative I e naught t. That's on top, and in the bottom you get e to the I e naught t times I, right? Minus I e to the negative I e naught t. Okay, wonderful. Why don't we invoke that 2? Let's bring this 2 inside, so it's e to the negative 2I e naught t over h bar. I don't know why I'm still writing that. Can drop that overall phase at any time. ei e naught t plus e negative I e naught t over 2. And here I can write it like this, e to the I e naught t. I think I keep forgetting h bar here, yes. Minus e to the negative I e naught t over h bar over 2. And there is I here, right? I. So let's multiply top and bottom by negative by I. So I get I in the bottom, and here have another I. So I get I squared. All right. So now what is this? This is just the cosine of e naught t over h bar. Okay, this is just the sine of e naught t over h bar, and I squared is -1. You know that. Oops. So finally, I can write down my answer. Psi at time t equals to, do I need to, yeah. Let's drop the overall phase, which is this. Let's forget about that. That's going to be cosine of e naught t. It's not a mistake to keep it, but you don't have to. And here's -1 times sine of e naught t over h bar. Okay, now one more thing before we proceed. We need to check, just to make sure our algebra is correct, that when t equals 0, you get we get correct initial state. Just check psi at time t equals 0 is 1, 0. Yes, check, it works. Doesn't guarantee that everything we've done is correct, but at least there is no obvious algebraic mistake in this. Well, I know it's correct, and just show you what you might need to do to check for errors. All right, next, calculate expectation value of Sx as a function of time. All right, that's pretty much standard. Sx is psi at t, Sx, psi at t. Do we have any questions about everything I've done so far? No questions at all? Okay, since there is a silence, I will proceed further. Okay, where is my psi? Here's my psi, so I'll make a bra out of that. I'll just transpose, and Complex conjugate, there's nothing to complex conjugate here, so I'll just write like this: cosine E naught t over h bar, negative sine of E naught t over h bar. What is Sx? This is h bar times 0, 1, 1, 0. This is sigma h bar over 2, by the way, yeah. That's sigma x here. And multiply by the ket. Cosine E naught t over h bar, negative sine E naught t over h bar. All right, let's multiply, I guess, let's multiply this matrix by the ket, and I will keep h bar over 2 outside first. Let's not touch the bra yet. Okay, what's the ket? That's going to be negative sine E naught t over h bar, and then cosine E naught t over h bar. Okay, now we multiply this ket by the bra, we get h bar over 2, and here it's negative cosine E naught t over h bar times sine E naught t over h bar, and then minus another thing, right? Same thing again, right? Sine times cosine. Okay. So I can rewrite this as negative h bar over 2 times 2 times 2 cosine. Let's do 2 cosine E naught t over h bar times sine E naught t over h bar. Well, we know that this is just the cosine of double argument, so it's going to be negative h bar over 2 sine 2 E naught t over h bar. Okay, so now why was this problem on the test is just to demonstrate that for the operators who that is not commuting with the Hamiltonian, the expectation value will be time dependent. So we see that time explicitly in over here we see the time explicitly in the expectation value of Sx. So it's going to oscillate. All right. Any questions so far? All right. If there's no questions, you should be afraid to ask questions. You can type them. You can unmute your microphone and tell me. If there's nothing else, let's move on to the next part of this problem. Does the expectation value Sy depend on time? Explain your answer, but do not calculate expectation value of Sy. Okay, let's go back and look at the eigenstates of the Hamiltonian. Look here. This 3e naught is really what? It's the same as minus y, right? This is minus y ket in SZ basis, right? And e naught, this is really what? It's just plus y ket in SZ basis. So we see that the Hamiltonian and Sy operator, they share eigenstates. They have the same eigenstates. And since they have the same eigenstates, they commute. So we can write here that since Hamiltonian and Sy share eigenstates, they commute. commutator HSY has to be 0. Okay, and because of that, we know that therefore d over dt. Remember that we derived that for a operator, for random a operator, which is I over h bar psi t commutator HSY psi. Oops, that's psi t, right? This is simply 0 because that commutator is 0. And that means that expectation value of Sy is constant. It does not depend on time. Okay, so that's pretty much it. Any questions? All right, if there's no questions, the last part of this problem, which is really the easiest one. See, the Hamiltonian of the system is now modified to include an additional small oscillating term. And the hint is possibly due to electromagnetic field. What's the resonant frequency of such system? I didn't write any expressions for Hamiltonian on purpose to make it, to hint to you that you don't really need to do any calculations in this part. Look, we know that if you measure the energy of the particle for this Hamiltonian, right? Well, that is before you added time-dependent oscillating term. You will end up with either 3E0 or E0. So essentially, you have two-level system with energy E0 as the smallest one and energy 3E0 as the largest possible energy for the particle in that Hamiltonian. Okay, what is the difference between those two energies? That's delta E, right? That's 3E0 minus E0, which is 2E0. So for resonance transmission to occur, that is for the transmission with highest probability. For example, the particle in the lowest state to be transferred to the upper state with energy 3E0, the particle would need energy which is exactly 2E0. So the energy of the photon here has to be equal to 2E0, and that energy is h bar omega, which is the frequency of that oscillating term. So essentially what you need to do is h bar omega equals to 2E0. So the frequency omega is just 2E0 over h bar, end of story. Okay, any questions? Guys, any questions, any remarks? So how does, okay, do you have any questions regarding this test? Do you have any remarks or, some comments about how this online thing works on your end? It's pretty much new to me. This is the first time I'm doing this, so I'm quite sure it could be a screw up at some point. Any remarks, any questions? You can type, you can talk.
I know it sounded pretty good, and we were able to see everything you were writing for the entire call. So it worked really well on our end.
Okay, that's encouraging. So
I also think it worked very well.
Wonderful. Thank you, guys. Thank you very much. So if the if our superiors decide to switch to online, which looks more likely than a couple of days ago, who knows, then we will do that.
And do you have a question in the chat line from Jordan?
Oh, okay. I sort of wondering, how do we know SY can be used with Hamiltonian probabilistic impulse? How do we know that that Sy commutes with Hamiltonian. That's because I noticed at the very beginning over here. See, I looked at the eigenstates of the Hamiltonian. You see how they look like? 1 over root 2, like 3 naught in SZ basis is 1 over root 2, 1 over root 2, 1 negative I. But this is minus y ket. That is the eigenstate of the Sy operator corresponding to the state in which the y component of the spin is negative h bar over 2. Okay, and same thing with E naught. This is the another eigenstate of the Hamiltonian, but look, it just happened to coincide with plus y ket, the one which we learned at the very beginning of this course. So that means that really eigenstate of the Hamiltonian, 3 naught eigenstate of the Hamiltonian is really is the same as minus y, which is eigenstate of Sy operator, and E naught is also E naught eigenstate. So which means that Hamiltonian and Sy have identical eigenstates, and remember that means that they commute. This theorem we proved in class. It works both ways. If two Hermitian operators, non-degenerate Hermitian operators, if they commute, they share eigenstates, and vice versa. If they share eigenstates, they commute. We know that from we proved that theorem for non-degenerate operators, right? Non-degenerate, and those two operators in this case are not degenerate. For degenerate, it's a little bit more complicated, but works very similar. All right, so that's how
Can I add a little bit to this?
Sure.
The way I understood it is that when you look at the Hamiltonian, you realize that it's proportional to diagonal term plus a term which is you recognize as being S, two-dimensional representation of Sy. So Hamiltonian is explicitly in terms of Sy. So that's why Sy commutes with it. This. When you look at there's a minus I and plus I in it, that means that there is a Pauli matrix that corresponds to Sy.
Yes, you can say that as well. You can actually see that you can express Hamiltonian in terms of Sy. But yeah, that's another way of thinking about. So essentially, that means that eigenstates of the Hamiltonian the same as eigenstates of Sy, and they are stationary states, right? They are only acquiring overall phase, and therefore the expectation value of Sy should not really be time dependent.
In the chat, you have question from Yudlanju.
I'm sorry, what? In the chat, I have another question. Yes, thank you very much. All right, I don't know why in the problem 2a the coefficient can be ignored. Oh, that's because, well, you can write it. There is no mistake. There is no error to write that coefficient, right? But this is overall phase, right? That coefficient multiplies both components of my state at any time. You can you see this overall phase. Yes, it's time dependent phase, but it's the same thing. This is something you can factor out for both components of my vector, and that means that in any meaningful calculations you can do with psi at any time t, this overall phase will cancel out. By meaningful, I mean you can, if somebody asks you to use that psi that you obtain to calculate expectation value of whatever, or probability of being in whatever state, you name it, in whatever calculations you do with that state that you can actually compare with experiment, that means referring to some expectation values or probabilities or something like that, that overall phase will always disappear. It will always cancel out. And that's why we, as a rule, we may neglect that. We may just we may not write it. But again, as I said, there is no mistake there's no error to write it down. You will not get any points off if you keep it to the end. All right, and that's fine. That's fine to keep it. But for the simplicity's sake, I just dropped it at some point. All right, any other questions? All right then, guys. Then I will see you tomorrow on regular class time in the class, right? So we'll continue to meet in person in class until Georgia Tech decides to close down campus, which I think will happen at some near future. But for now, I think they're still not closing the campus, so we'll meet as usual tomorrow in our classroom. All right. Thank you very much, and have a good night. Oh, my office is W108 in Hawaii. Okay. How do I turn this down?